Thank you for coming down and hearing us and spending your Saturday at this conference. I know you have a lot of fun things that you can do on a Saturday instead of coming for a conference. So yeah, thank you for coming here. So I'm Piyush. I'm the lead of the data pipeline, data platform team within Criteo's AI lab. And I'm going to talk you through some of the ideas that we've been working through to try and build a data platform. So this is the agenda for today. So there's a little bit of background, for those of you who don't know about Criteo, give you a little bit of sense of what we do, what are the challenges involved. And then I'll really dive into, what are the various building blocks that you need to put in place as part of speeding up the iteration of your machine learning workflow, talk about where we are on that. And since this particular talk is a big data talk, I'll kind of zoom a little bit more into the big data aspects of it and what are the bottlenecks that our users face, what are we trying to build and stuff. And then at the end, I'll kind of leave it to sort of talk about what we're planning to do going forward and stuff. So what is Criteo? For those of you who don't know, Criteo is an advertising company, an online advertising company, and we're really trying to connect users to products that they love. And big data and machine learning have been sort of core to Criteo's success from the very beginning. It's not just something that we've started to do, going forward or like recently or something. So it's been something that's very core to our company and our product from the get-go. So we've got a couple of really interesting aspects here. So one set of aspects is like really interesting machine learning problems. So we're trying to tackle problems, in click prediction, in recommendations, in auction theory, and a lot of other stuff. And I think we'll give you a little bit of flavor of that today afternoon. We have a talk from Ivan from the Criteo AI lab, and he's going to talk about some of the more machine learning oriented work. But the other challenge that we face is the fact that a lot of these machine learning problems that we're trying to solve, we're trying to also solve them at really large scale. And the scale can come in various aspects. So one aspect is the fact that data sets that we deal with are hundreds of terabytes in size. The event streams that we're dealing with are 50,000 to 100,000 events a second. So there's a lot of really large scale involved there, which basically spills over into making sure that you're able to do optimizations at scale. When you're deploying these algorithms out in production, you need to run inference at really large scale, and also in some of our applications, your inference needs to be really, really aggressive in terms of latencies and stuff. So for example, when you're putting out, you're competing for real-time bids, the latencies are, on the order of a millisecond or two. So your inference has to be really fast. So what this kind of feeds into is the fact that it's really essential from an infrastructure perspective to have the right tools in place, the right services in place to actually allow various practitioners within the company to actually build these pipelines in the right sort of fashion and the right scale and stuff, which is where the infrastructure is so important. So when you think about the machine learning workflow and the tools, it is instructive to take a step back and try to think through, what is the typical workflow? And you've probably seen, variants of this in various other places and stuff. Simplistically, you would come up with, an idea for a machine learning algorithm or an idea to, tweak your feature engineering. You'd start off with exploring, the data sets that you have available. You would build a training data set. Then you go on to actually, building out your model and testing it out, train it and evaluate it. And then you'd actually take it out to, deploy it in production. You would monitor it to sort of see how it compares against, either your existing algorithms or against run it in an A/B test or something on that, fashion. And this sort of idea is fairly common across the industry. There's a lot of companies which are trying to build platforms which will try to speed up this whole process. Uber, Airbnb have put out blog posts and articles and talking about this. Databricks, which has built Spark, is also building out a product called MLflow, which kind of tries to tackle this. And the core essence of it is there are two kinds of complexity that you're typically dealing with when you're going through this workflow. So one of them is sort of the accidental complexity, and the other one is sort of the inherent complexity. So the inherent complexity is really the complexity which is centric to your problem, right? So you're trying to basically build a really complex machine learning algorithm. So there is a lot of inherent complexity in that. But the complexity that you really want to guard against and fix is the accidental complexity, which is just the fact that, it can take your users a really long amount of time to basically dig into your data sets because of the infrastructure available. It might take a lot of time for you to actually build, these pipelines and stuff because your infrastructure is like, maybe not as stable as it should be. You might have users who are trying to compare different runs of their algorithm, but they have to keep track of they have to keep track of the various parameters and stuff by hand because you don't have a service in place which can kind of keep track of the various hyperparameters you've tried as part of this. So Criteo as a company is also fairly mature in terms of the the tools and the libraries that we have, and we've been doing big data and machine learning for a very long time. So we've got a lot of these building blocks which we already have in place, and we tend to use a mix of open source as well as in-house projects and products. And we've got a lot of the common ones that you would probably see, like we use Spark and Presto, Hive, and stuff like that fairly heavily. The ones that I'm going to really touch upon out here are the fact that, okay, when it comes to, exploring data, we've got a really nice catalog service called FatCat, which I'll talk about in a minute. We've also got, when it comes to like users actually trying to generate their data sets and stuff or experiment with models, we've got a hosted Jupyter Notebook sort of service, which you can actually use so you don't have to spin up Jupyter Notebooks on your laptop and try to train, your 50-layer deep TensorFlow model on your machine. You can actually go out and run it on a more powerful machine. We've also got a lot of people who are trying to experiment with TensorFlow in a distributed fashion. So we built a library called TF-Yarn, which allows you to actually kick off and run your TensorFlow jobs, at scale. As well as, we have libraries and services in place for you to actually run different versions of your model, compare different runs, keep track of A/B tests and stuff. So we've got sort of in-house services called Test Framework and another one called Papa Tool, which kind of help you do that. So the part that I'm really going to zoom into now is the actual exploration of data and the generation of data sets and what are the problems there, where are we at with respect to the tools and stuff there. So the first part, I guess, which kind of comes in, there's two big aspects to the data picture, right? So when you come up with an idea for a machine learning algorithm or an idea for feature engineering, one of the first things you're going to do is try to explore the data. And then the next thing you're going to get on to is actually generate the data sets that you need or like enhance the data sets that you need, right? So when it comes to data exploration, one of the key, there's a few key things that you want to do as a user, right? You want to explore, what are the data sets that I have available in the company? What are the ones that I can actually look at to pick up and use, right? The other part, once you figure out which data sets there are, you want to know what are the SLOs on these data sets. Am I going to be trying to build a pipeline around a data set that, might not actually be, supported in production? So if I build this pipeline and try to put out my model in production, like 3 months down the line, the data is not available, that's a problem, right? You want to know also about what are the fields available in a given data set, right? So you might want to actually dig into that and see, okay, I actually really need this field which tells me about the sales data for a given model. So you need to have a data set which gives you that, right? So there's a lot of these aspects which you kind of want to dig into. And we've got a tool called FatCat, which kind of allows you to do that. And FatCat's basically a data sort of catalog that we built in-house. Apart from FatCat, something that you also end up doing quite often when you're trying to build or explore your data sets is to try and run, get some data samples. You want to try and slice and dice your data to sort of see, what it looks like. You might want to pull that data into a Jupyter notebook and try to explore it and stuff. So we provide a bunch of standard set of tools for allowing people to do that. So we've got, things like Presto, we've got Spark, Hive and stuff. And we've also built connectors between engines like Presto and Jupyter Notebooks. So you can have, a machine learning researcher or a machine learning engineer who wants to like spin up a Jupyter Notebook, pull a bunch of data in via Presto query, and then proceed with actually iterating on their model in their Jupyter Notebook and stuff. So there's a couple of things to call out here that we are missing. So one of them is the fact that when it comes to the actual features and stuff that you might want to explore, we don't have a very good sort of catalog of all the features that are available at Criteo. We don't have a really good set of documentation for the fact that, okay, we have this particular the sales in the last 6 hours kind of feature, but what does that actually mean? So a lot of the times when you have researchers or when you have engineers who are trying to figure out which feature they should use, they need to either know that from hearsay or spend a bunch of time digging into it. So that's something that we don't really do very well. But in terms of just the other data exploration part, we seem to be doing a pretty good job. So the next part, which is where the rubber sort of hits the road, is the actual generation of feature data. And this comes in like a couple of angles. So there's one angle which is really around generating your training data sets, right? And this can be in two parts. So one part of it is when you're trying to generate a data set for training, sort of in an ad hoc fashion, right? So just think you have an idea that you want to use, you want to create embedding vectors for user events. So that's something that maybe we are not doing regularly in production. So you have an idea as a researcher. So you might want to generate an ad hoc data set around that use case. And the other one is, a little bit more sort of scheduled, right? So if you figure out that, okay, we've tried out a model, we've A/B tested it, it seems to be working really well, so we need to do this on a regular cadence, right? So you might want to have a regularly scheduled job to actually do this. And both of these are really batch workflows, right? So you're kicking off and running a job sort of either in an ad hoc fashion over a really large data set, or in a scheduled fashion, again, over a large data set, but that's done on a regular schedule, like every day and stuff. For this particular set of tasks, we've got a bunch of tools at Criteo, and we tend to use a lot of like standard open source tools for this. We use a lot of Spark. At Criteo, we're using Presto for experimentation. We end up using, we have a few users who are using TensorFlow to actually generate some of these ad hoc embedding data sets and stuff. The parts which are really hard for our users sometimes end up being either around the scale. For example, if your input data sets are hundreds of terabytes in size, you have a lot of knobs to tune when you're trying to run your Spark job. So we have a lot of users who run into those issues. We have a lot of issues, or a few issues when it comes to actually like, building your pipeline and actually putting it out in production, because we have a few things which are kind of sort of slowing down the iteration speed there. And this is something that our data infrastructure team has been banging at quite aggressively, and I think Justin and Guillaume will be talking a little bit about the directions that they're thinking about over there. The other aspect is around when you're actually trying to, so when you've trained your model and you've built it, and you put it out in production, and you're running inference on production for on real user traffic which is coming in. So you need to compute your features a lot of the times there. And there's two parts to this. So one of them is really around computing features. You might have features that you want to compute in batch, so you want to pre-compute some of these features because you don't really care about how frequently some of this is changing. So the recency of the data doesn't matter so much. So in which case, the computation of this is really similar to the training set data generation. You'll schedule it as an online, like an offline job on MapReduce, and you'll basically compute these features and put them and make them available online for actually using on your inference. The other part is really in terms of like the near-time features or the short-term features, right? And some of these are things like, you might care about the number of displays that a particular user has seen over the last 1 hour, or you might care about the websites that a user has visited over the last few hours. So in some cases, in some models, the recency of the data matters a fair bit. So in which case, you might want to compute a lot of counters and a lot of features in a more short-term sort of fashion. And for us, on this particular point, the solution that we have is a little bit, it's a little bit ad hoc. And I'll get into that in just a few minutes. So one of the things that you want to sort of understand and try to address when you're trying to build any piece of infrastructure software is, what do your users really want? And that was one of the questions that we were really trying to understand when we started this team, and we were trying to figure out where we were going here. And this was a especially important question for us because our users were a fairly wide range of people. So we have users who are, some of them are researchers within the organization. Some of them are machine learning engineers who are trying to build pipelines and put them out in production. And some of our stakeholders are people like upper management who care about the governance of an issue and governance of features and stuff like that. So we basically spent a bunch of time talking to a lot of our users, trying to understand what are the important set of features and what are the core things that they really want us to build, right? And there were a few things that popped out. The top two were the two primary ones, which was, one of them was around trying to be able to experiment with adding features really quickly. So something that a lot of people run into at Criteo as of today is, if they're trying to compute features in the online fashion, like the short-term features, it takes them a lot of time to do that. The time that it can take you can range from a week in the best case to a few weeks, which sometimes is unacceptable. You don't want to spend like 3 or 4 weeks to actually get some of your features out in production. You might want to be able to iterate really quickly on it, because it comes back to the figure I showed you earlier, right? Like, you want to experiment with your features, so you don't want to spend 3 or 4 weeks on one of your steps, because that's going to slow down the whole cycle, right? So you want to be able to move really quickly on that cycle. So that was one of the issues, and the other one was around being able to compute features in a unified fashion in online and offline. So what I mean by that is, when you're computing the logic of your features, a lot of the times you're trying to compute aggregations over a period of time, like over 1 hour or over n hours, right? So in an online sort of setup, you might have a particular way you want to do this. Like, you might want to compute counts, or you might want to compute a count min sketch in case of approximate features. But the same logic, you might want to apply it over a longer time period. So when you have long-term features, you might want to still compute a count min sketch, but just over a longer time period. So instead of computing it over 1 hour or 6 hours, you might want to do that over 1 day or a week of data. So one of the things that a lot of our users wanted to do is, they wanted to make sure that they write this logic once and they don't have to run it twice, and they don't want to re-implement it twice. And there were a few other aspects around, discovering features, being able to figure out what are the documentation of features and stuff like that. There were aspects around governance, where you want to know whether a feature is experimental or not, whether it's a production-ready feature or not. If you're relying on a feature that's being built by another team, what is the SLO? Is this going to be reliable? Can you actually build a model around it and stuff? So what we tried to do was, we tried to focus on the first 2 points, which were computing features in a unified fashion and adding them quickly. And what we decided to do is actually build a solution around that. Start off with these 2 primary use cases, build a solution around this, and then we could try to make sure that we build a solution maybe with an eye towards the future, so that we can include a lot of these other aspects in the solution as we go along, or the design can actually accommodate some of this stuff. So the reason we chose this was that it was really pressing for our clients, first of all. Like, a lot of people were really getting slowed down when it came down to adding short-term features, adding near real-time features for machine learning. So that was one of the reasons that we decided to focus on it. And to take a step back and to really understand why this was a problem, right? So the way things are done currently at Criteo, when it comes to computing a lot of these short-term counters, that ends up being in sort of the end set of web applications that we have, which are sort of on the edge. And these are C# applications, which we call TLAs. What that entails typically is, say you have to add 4 or 5 features. Say you're adding features for the displays, or the number of sales and stuff for partners or for campaigns. You might need to end up touching a bunch of these web applications. You might end up having to touch 2 or 3 of these web applications to add these counters. So that ends up meaning that you have to go out and write code in C# for a few of these applications. You need to wait for 3 or 4 of these applications to get deployed to production, till you can actually use your features, till they're made available. The other aspect is, a lot of the times when you're adding features to start off with, you don't really know whether they are going to have any benefit in terms of business impact. You're really experimenting with them to start off with. You just want to add these features, then you want to train your models, build your models. Then you actually figure out that, oh yeah, these features are really useful and I want to keep continuing to have them, right? The problem with this current approach that we have is the fact that you're ending up going out and changing a bunch of code which is running in production, which is bringing in revenue and stuff. So you're going out and adding a bunch of experimental features and experimental code out there in these systems, which can be a bit of a risk, right? You need to make sure that you have the right checks and balances in place, but then that slows you down when it comes to experimentation and iteration on the experimentation part. So the other aspect was because of the fact that these applications are written in C#, you run into one of the problems that I touched upon earlier, which is the fact that, say you're trying to compute a complex algorithm, right? Some of our users wanted to compute a count-min sketch of approximate counts. So you have to compute this for your online side of things. So maybe you're trying to compute these counts for the last hour of data or last 2 or 3 hours of data. So you'll end up implementing this algorithm in C# once and you push it out in prod. But then you want to compute these same sorts of counts over a longer period of time, over a day or over a week of data, right? In which case, you basically have to go out and compute this on a bunch of batch jobs. And typically, most of our batch workloads run either on Spark, so they are typically like some sort of JVM-based engine. Either they're running on Spark or they're running on MapReduce, right? So you need to compute this, you need to implement this algorithm multiple times. You need to implement it once in C#, you need to implement it once in the JVM side. You also need to sit down and worry about the correctness. And we've had a few people run into issues with respect to just the correctness because of the subtle type differences between C# and Java. So that tends to be a bit of a problem. So that's really what we decided to focus on. And this is sort of the direction that we are sort of thinking out in terms of this solution. So the high-level idea is this. So our users basically will express their computations in a DSL, where they express these are the sets of features that I want to compute. We pick up that DSL in a service, and we end up kicking off a streaming job, which is going to run and compute these features. And it's going to compute them over whatever period of time that the users define. It's going to compute these counters, and it's going to write them out to the appropriate SQL, NoSQL stores like Memcache or Couchbase or whatever. So what that looks like pictorially is something like this. So you have a repository of the various sets of features that you want to compute. That gets picked up by a service that we call the Feature Factory. Doesn't have a nicer name as of today because we couldn't think of one. But we pick it up in this service, and that service is basically going to pick up and kick off the corresponding streaming computation job. So each of these DSL files gets scheduled as like a separate streaming compute job. And each of these jobs is going to subscribe to the relevant Kafka streams. So it's going to pick up, depending on what features you want to compute. You might say, I want only access to the advertiser scene, or you might want access to the clicks and the displays or whatever, right? So you specify which streams you're interested in. We pull in those streams, compute those features, and then we end up writing out this data to Memcache or to Couchbase so that it's available for the inference side, on the online side of things. One of the things that we also do in this service is to actually pull out a lot of the metadata that users will specify with respect to a service. We pull out that metadata and then end up writing it out to a store. So just a quick primer on Flink, because that's the engine that we're using for computing these features. It's a nice framework to actually compute both streaming sort of unbounded data sets as well as bounded ones. We use it pretty extensively at Criteo for streaming applications, and it's something and it's a service that is used quite extensively in the industry. They have a lot of really nice APIs. They've got a data streams API, which is more like a fundamental building blocks kind of API. They also have, SQL-based APIs and stuff. The reason that we've chosen Flink, and a lot of companies are choosing Flink, is they have a lot of really rich abstractions. They have concepts of time windows, where you can say you have a fixed length window, you have sliding windows, they have support for checkpointing of your jobs. They run on a very wide range of frameworks like Yarn, Mesos, and Kubernetes and stuff. So that's kind of one of the reasons why they have a lot of traction, and that was the engine that we ended up choosing. So one thing to call out, taking a step back, is the solution that we prototyped so far is largely just for the online features, but it could just as well be extended for computing batch features. And the idea would be really similar. You would just take the same sort of DSL files, and instead of just issuing the online jobs, you could also pick up the same DSL files and kick off these jobs on and on a batch framework like Hive or Spark SQL or any engine which supports a SQL-like interface. And those jobs will basically run, compute your data sets over the relevant time periods, and write out the data to Hadoop. So one of the central aspects of this is the DSL, and this is some of the parts that the DSL consists of. So each DSL basically is computing a group of features at a time. So you could consider it as like a data set that you're computing at a time. And this is broken up into a few parts. So one part is basically the metadata, which describes the set of features. The other part is how you actually store this data, how do you write it out to Memcache or Couchbase. And then the last part is how do you actually compute the features, how do you pull the data that you care about, how do you actually compute each and every feature. So let's take a look at all of these parts at a time. So the first part is really the metadata and the storage. So in terms of metadata, you have an owner for a team which owns this data set. You might specify that a feature is experimental or not, so that consumers can sort of pick it up if they realize that it's experimental or production ready and stuff. You can specify documentation for your features. You have storage involved, so you can specify how you want to actually write this data, where do you want to write it out. The next part is actually how you compute these features. And this comes in two parts. So one of them is how do you actually pull the data for your features, in which case it's basically a pure SQL query for us, where you can say, okay, I'm interested in the advertiser stream, the billable display stream, the click stream. So you can pull these data sets. For each of these feature groups, you will have a particular field that is going to be the identifying field. So in this case, I've taken an example for a campaign set of features. So the ID field is going to be the campaign ID. So you're going to group by that. And the last part is actually how you compute these features. And this basically comes down to, what is the SQL operation that you want to perform for computing that feature. So this could either be a SQL expression like the one I've shown up here, or it could be a user-defined aggregation function. In case of a UDAF, the nice thing is the fact that you could compute things in a more arbitrary fashion. You're not restricted to just computing a SQL statement. So one example of this would be if you're trying to compute embeddings and you want to call out to some service like TensorFlow serving. So you could wrap that up in a UDAF and make calls out to TensorFlow serving to compute these features and stuff. So basically your file would consist of a bunch of these features. And what we would end up doing in our service is parsing this DSL file and kicking off a SQL query, which kind of looks something like this. So basically you will select the relevant features that you have. You might have a time window, and then you're going to pull the data from the base query that you specify, and you'd group by and the campaign ID as well as the time period. I'm not going to go into the big DAG, but what ends up happening is Flink is going to take this query and it's going to spit out a really large graph that it's going to actually kick off and run. Flink, the engine, is really smart about making sure that it sort of combines operators and stuff and doesn't really break it up unless needed. So in terms of storage, this is kind of what it looks like. You have a couple of ID fields. You have a campaign ID and a timestamp, which is really, in this case, the sort of the primary key. And then you'll basically write out unique values for each combination of this. And just to wrap up, so I think there's a few things that we're trying to bang at on this topic, especially on the online side. So we want to work on adding custom triggers so that you can actually end up computing these data sets and writing them out more frequently than the time windows you have, enhancing some of the support which we have with respect to Mesos and Azure storage. We are also working on refining the interface in terms of maybe integrating a little bit better with some of the initiations that we have at Criteo, as well as improving the UDAF support so that we can actually write a UDAF once and run it across different engines. Because currently our UDFs only run on Flink. Maybe you could write it and run it across and run it on Spark or Presto or Hive. And then the last part is to actually build out the other parts of this, which are like the batch engine, the backfill support and stuff like that. So I think I'm way over time, or a couple of minutes over time.